All right, we're going to solve this Laplace transform differential equation problem. We have a step function as part of the non-homogeneous term on the right-hand side. And so we need to see an example of how to deal with that from start to finish. We've seen some examples of how to take Laplace transforms and how to do the inverse that comes out. But let's do a whole problem here. So we have a step function where something is turning on in the forcing at time pi. So we are expecting a response in the solution at time pi, and we'll see that as we get to the solution. So let's start. We know the first step is to take the Laplace transform of both sides. We have an s squared capital Y minus s y at 0 minus y prime at 0. That's the Laplace transform of y double prime. Plus 4 capital Y, that's the Laplace transform of y, of 4 times y. The Laplace transform of sine of t is 1 over s squared plus 1. And the Laplace transform of this step function, now this is a good news step function. Good news in the sense that the function itself that's multiplied by the step function is shifted by the same amount as the step function. That means we can use line 5 in the Laplace transform table directly. And that gives us an e to the minus pi times s over s squared plus 1. You can think of that exponential as coming from the step function, and then we have the 1 over s squared plus 1 from the shifted sine function. So there's our Laplace transform. We know the next step is to solve for capital Y. This is s squared plus 4. The initial conditions are both zeros, so fortunately that goes away. 1 over s squared plus 1 plus e to the minus pi s over s squared plus 1. Finally, the Laplace transform of our solution is 1 over s squared plus 4 s squared plus 1 plus e to the minus pi s squared plus 4 s squared plus 1. Now, normally at this step, we have to decide, do we need to complete the square or separate with partial fraction decomposition? And in this case, it is a partial fraction decomposition. And fortunately, it's the same partial fraction decomposition in both terms, which is good news. It doesn't always work out like that. In nastier problems, you have to do two different partial fraction decompositions, or maybe a partial fraction decomposition in one place and a completing the square in another place. These can get messy, unfortunately. But I've gone ahead and I've done the partial fraction decomposition ahead of time. This turns out to be a 1/3 over s squared plus 1 minus 1/3 over s squared plus 4 plus e to the minus pi s times 1/3 over s squared plus 1 minus 1/3 over s squared plus 4. Now this is mostly ready for us to invert it off of the table. The only issue is that old trick that we're going to have to deal with. Instead of a 1/3 in the numerator of the s squared plus 4 denominator fraction, we need a 2 up there. So we multiply the numerator and denominator here by 2, and we will have this in a form that we can use the table on. So let's do a little bit more writing. We have 1/3, 1 over s squared plus 1 minus 1/6 times 2 over s squared plus 4. That gets us the 2 that we need to go along with the 4. 2 is the square root of 4. Now that looks like something that belongs on our table. And in here it's the same. Now we can use the table, we can invert all of this. So the inverse, well, that's not an equals anymore. This is now going to be y of t, the solution, equals 1/3. The inverse of 1 over s squared plus 1 is sine of t. And the inverse of 2 over s squared plus 4 is sine of 2t. So this is minus 1/6 sine of 2t. And then we come to the part with this exponential. We know the inverse of something involving the exponential is going to give us a step function. So we're going to have plus step function t minus pi times. Now the inverse of the 1/3, we have sine of t. But now, the way that the table works in line 5, remember we replace what we would normally have as the inverse. We replace the t with t minus pi. So normally that inverse would just be a sine of t, but because of that exponential and the step function stuff, the inverse, the t becomes t minus pi. It's shifted by pi minus 1/6. This would be the sine of 2t if not for that exponential, but with the exponential, it's the sine of 2 times t minus pi. And that is our solution. And it's big, I guess, and maybe ugly. But what we do have in this solution, as part of this solution, is a step function. We do have something turning on at time pi. So an extra thing happens at that time, which makes sense because we were turning on some extra forcing at that time. So it makes sense to see a response in the solution with a step function u of t minus pi.